That is absolutely true. So hopefully we can get through the whole chapter. Did we get through the whole chapter last time? I feel like we did. Uh,
Yeah. Also, if this is just like rectangle intersection, it shouldn't be too hard.
yeah. So we, did we go through this? Oh, we did talk about, yeah, I remember, I'm remembering this. Yeah, okay. We did cover that. What? Okay, here we go. So yeah, we'll go from having just a simple pinhole to having a more useful camera model. Um, so we have raycasting algorithm. I'm just gonna go ahead and start. Yeah. Um, mm, so we're going backwards from the image planes through the aperture out into the scene. P plus omega t. It finds the first scene point X that intersects by that ray. And by using rays, we get perspective correct projections automatically without having to do any fancy, crazy math. Um, I guess projections aren't crazy. They're just a bit more complicated than a nice ray traversal is. So, um, we got a render function. We define a camera. We define an image plane with some parameters like the width and height and the image type. We just render and we're done. It's great. Go home, everyone. We're done here. No. We'll have to figure out how this render function works. Yeah. 160 by 100 pixels is still 16,000 pixels, so it's not like it's a impossibly small image. It's just compared to modern computers, it feels very small. Um, um, so surfel is introduced as a term. A surface element contains the intersection, position, normal, and material information that will be useful. Um, hmm. So a pointer to the surface element. So when we do a raycast, we get a surfel back, or null if we didn't hit anything. Universal surfel for the base classing. Um, we have our render function. We go through each pixel individually. We get a primary ray, and this gets our, this gets the where was it? The point P in vector W, and it puts the values in there, and then we'll set our image at pixel X and Y using the luminance function given a point and vector. Or, would that be a normal? Probably. Okay. Yeah, for now, if ray hits the surface, helper function sets the radiance of the pixel to 1. So if it hits something, it'll get white and or a radiance of 1, and if it doesn't hit anything, it'll have a radiance of 0, effectively being a black and white image. A perfectly black and white image, I should say. So, here we have that function. Um, so find first intersection is our hmm. Oh, so this is generating the ray at a position point at a point P in a direction W. Okay, yeah. That makes more sense. all points, those points, you could subtract them. The set of all points on the sphere, if you subtract the point on the sphere with the center of the sphere and then take the absolute value, it should equal R because all points are equidistant from the center, all points on the sphere. So that's what this is expressing. Explicit equation for array with origin P. Yes, this is our equation for array. P plus T hat, or T times omega hat. Uh, okay. So what we can do is we can substitute our equation for a point on the array, given T is a parameter, like a parametric, and we can substitute that in for X and then solve for this. And when the answer is, I guess I don't know what they're gonna do. Let's keep reading. Yes. So we substitute it and then simplify. Yeah. So vector v is equal to p minus c. So, okay, yeah. We want to get rid of this absolute value, so we square both sides, and then we can move the r over to the other. Expanding the dot product, the self dot product. Oh yeah, I guess that works. Oh no. That is, I've never thought about expanding a function with vectors in it like this. Or I maybe have and I just forgot. I guess this is a quadratic. This same math appears in ray tracing in one weekend. It's just it. So yeah, I have seen this kind of math before. We have a quadratic equation because it's a quadratic polynomial. Uh, Quadratic
Think
formula.
about it. Like, what does it mean to have like power of two for a vector?
Yeah,
It's already a dot product.
yeah, that is an odd thought. See, I intuitively think when I see this that if you substitute a point in, subtract C, and if it's less than R, less than or equal to, I should say, it is within the sphere. Therefore, you know it's intersecting. But what that doesn't tell you is where it's intersecting. And so I can see why you want this formula over here, the quadratic formula, when by substituting A, B, C with the various parameters here to get our roots, i.e., the points that intersect the sphere. Or no points at all, in which case, would you get an imaginary number, I get in that case? Probably.
Yeah,
I think so, yeah.
yeah.
That's a weird thought because it implies if a ray doesn't intersect a sphere, it still intersects the sphere just in the imaginary plane. Whoa.
Hmm.
Oh, I'm sorry.
Imagine what you could do with a warp drive and ray intersection. Okay, I'm kidding.
Yeah.
There's
Smallest root.
a couple people on the graphics programming Discord who are doing four-dimensional ray tracers right now. It's been interesting to watch. They say it's a trivial extension of three-dimensional ray marching, but I
Yeah.
trouble getting my brain around it.
Um, Yeah. So if A equals 0, then the ray does not intersect the sphere. It intersects it at a infinitely far away distance, aka not in the observable universe. Uh, so what an interesting thought. Okay. Discriminant is an imaginary number. Okay. Surfaces are oriented, thus single-sided. If the ray origin is inside the sphere, then it cannot ever hit the outside of the sphere, and we should ignore any intersection detected. Wait. Oh yeah, I guess with oriented surface, you throw out cases going back through a surface or from the inside of it. We do not want to consider that, so we just reject any case where the point minus the circumference is, yeah. If your starting plane is, or your starting point is within the sphere, then you just ignore any intersections found.
There's
Okay.
going to be like a decision for the type of renderer that you're making. Like
Yes.
I've done this before where I decided to like do something inside the sphere.
Yeah.
Or if you want to support
Um,
reflection or something like that, transparency.
yeah. It also only applies, it only really makes sense to have this when you have, what's the type of object that's a bounding shell?
Convex? Hull?
I
Convex?
guess convex hull sounds right.
No,
Uh,
well, yeah, a convex hull is bounding another object.
mm, I'm just trying to think of most objects that we have 3D models for that are like pe things people hold and touch, not like whole levels, but the small objects, they're they have a defined surface with an even number of holes. Oh,
Manifold, I think
you
you're
know what?
thinking.
There's
Yeah.
probably yeah, manifold maybe. There's definitely some math term. Uh, well, I'm kind of excluding two-dimensional constructs like lines and planes. I'm trying to think of just there's an inside and there's an outside to the object. And when that happens, your surfaces can be oriented because you assume nothing can be
Mm,
inside the object and still
mm.
have a meaningful value. This is as opposed to just flat planes and more scenery, large scale entities where you have it has a defined edge, and that edge is just because you can't render the world. I don't know. I'm kind of going off on a tangent. Um,
I saw a surface of what you're of not what you're talking about the other day where there was like a three genus donut, but it had no inside because it had like three holes on the side and then three holes on the top, and it like it's so weird. It's like a Mobius strip or Mobius strip, whatever it's
oh,
called.
oh, yeah, Mobius strip.
Klein bottle also
Those,
similar.
yeah, a Mobius strip is a piece of paper with only one side. It's
Right, but
a
now
really,
you can make it volumetric and put holes in it,
yeah, like the
and like yeah, and it has no inside or something like that.
wine bottle might be what you're thinking of. Is it this?
It might have been top. I know what a Klein bottle looks like. It didn't look
Okay.
like a Klein bottle though, because it looked like
Ah,
a three hole donut with but with six with three holes in the side and three holes in the top. So it could have been topologically like a Klein bottle, but like I didn't recognize it as a Klein bottle. Does that
it
make sense? Yeah.
it probably is not a Klein bottle, but another type of because there's multiple characteristics that make up these weird shapes, and a Klein bottle is just one of them.
Yeah. a generalization of the climate.
Yeah. So I think the way to describe what I was thinking of earlier is if you put a ray through it, it will always have an even number of intersections.
Mm, yeah, I know what you mean. I just don't know the name for it.
Yeah, because in that case, you will always if you intersect if you put a ray through it, you'll go in it, then you'll go out of it. And if you go in it again, you'll go out of it again. It's just a property of having an inside. And that's actually a pretty useful property to do math with. I remember reading a Kerbal Space Program article about some technique that they were like, well, this is going to be really hard. And then they remembered their shapes were, if you could do that with your object, then it made things easier. That's incredibly vague as to what it was being talked about, but I read that in 2013 and I don't remember the details beyond what I just said. Okay. So they're okay. I'm just gonna ignore the exercise because it seems like it's just a know your vector and math and linear algebra. Okay, so we got our sphere, the black outside and a white inside. Uh, so we want to do a rate plane intersection next. Um, And so we're going to do a similar process to above where we have some equation define the plane, and then we figure out based on a point and direction whether we are going to intersect it or not. So we define a plane as x minus c times the normal of the plane. So here we have an oriented surface. The normal indicates the orientation, and c is a point along that plane. Um, th yeah, that's another form of it. Wow, that is a thick equation. And I can't select it because it's a picture? Oh, whatever it is, I can't select it. The formula. So we substitute our P plus T omega and we calculate it out, rearrange it again, and then we get a much nicer looking T's equal to C minus P times the normal over omega dotted with the norm, not times, dotted with the normal. Can you cancel the norm? I guess you can't cancel the normals out.
You can't because it's a dot product.
Right, right. So this produces a scalar, and so it's scalar division. Yeah, that makes sense. That's it's been a long time since I've done like vector algebra properly.
By the way, did you understand why number 10, why equation 10 is?
Do I understand why what?
What logically why equation 10 is what it is?
Um, yeah, so that's actually a good point. No, I don't. I thought I did, and then I realized I didn't. Uh,
The dot product tells you how it takes two directions and tells you how, well, sort of. It t takes two directions and tells you if they are aligned or misaligned, or zero means they're orthogonal to each other. Right, so the normal is pointing out of the plane, x minus c. If it's in the plane, it's going to be some direction from c to somewhere else in the plane. Right, so it's going to be completely orthogonal to the normal. But if it's not in the plane, x minus c is going to be uh, not orthogonal to the normal. I don't know if that makes sense.
well, um,
Yeah, I think so.
yeah. Are you trying? Were you trying to explain it? Because that
Yeah.
does make sense. Because I'm just thinking about it. This equation, you take any point and you subtract x minus c, you get the vector um pointing from c to x. And if you dot
Mhm.
it with the normal, because it's in a 90-degree angle, you're
Mm-hmm.
going to get a zero value because the
Gotcha.
angle between them is a quarter of a circle rather than 90 degrees. Yeah, orthogonal. I guess orthogonal. Yeah, I guess that's the word for it.
Yeah,
Um,
you can relate that to the cosine of the angle between them too. Yeah, that's a good way to think about it.
yeah. And then for our substitution, it's kind of just we're extending it so that we can find where along that T that point would be. Yeah. And if it doesn't intersect, if you get a divide by zero here, then it doesn't intersect it. I guess how did you? Okay, there are four special cases, which result denominator is zero and the numerator is non-zero. Yeah. Rays parallel to the plane. Denominator, numerator are zero, then T is not a number. Yeah. Just like how infinity is not a regular number, T is not a number is also not a number. Yeah, okay. Hmm. So they so due to floating point math, the infinity and not a number cases should just fall out of the math. Interesting. Yeah, if T is less than zero, the ray is directed away from the plane, and so it only intersects it in a negative T. Uh, yeah, and then we want to cull out rays that come from behind the surface. So, yeah. And then we get to the thing that we end up doing for everything else, even though there are some very, very interesting uh, things you can do when you have implicit equations for geometry, aka signed distance fields, um, non-triangle representations of geometry. That's what I'm getting at. Uh, let's see how they explain triangle intersection. Uh, yeah. Triangle is a subset of a plane, so it sounds like we're just gonna take the plane equation and then constrain it. Um, hmm, interesting. So they're gonna derive one for a specific triangle, but then let us generalize it, which I guess if we want to, we can, but or I guess that, I don't know. We'll get there when we get there. So we consider a triangle where the three vertices intersect the coordinate axes x, y, and z at one unit away on each axis. And it's described with this lovely x plus y plus z equals 1 equation. Um, the center is going to be in the middle of those three, 1/3. The normal is going to be 1 over the square root of 3. That's funky. But then we have the same equation for the plane as before. Uh, C happens to be the center point. We established that. Um, P and omega is what describes the ray. So we take our ray intersection equation. No intersection in the cases where, yeah. Uh, okay. 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 So to get if the intersection exists, we take the t that was computed and then feed it back into our p plus t omega to get the point that is the intersection point. Um, so barycentric vector. Barycentric vector B is equal to x minus O. That is the vector from the origin to the unknown intersection point x. So whenever we see b hat, it's really x minus the origin. That is the vector from the origin to x. Um, I'm very interested to see what beautiful things will happen by using this redefinition. Uh, okay, first two components of B um, are x of P minus T x of omega, and B1 is y of B, or y of P minus T times y of omega. So they described that B2 could be expressed similarly, z of P minus T z of omega. X is on the plane, and the z component can also be computed by. So we can define the z, or the third component of B, in terms of the first two components, because we have the equation x plus y plus z equals 1. So we substitute our x and our y and move them over to the other side to get 1 minus x of b plus y of b. So all the rays strike within the bounds of the inner triangle. In the bound line, do so. Points x that also lie within a unit cube. Right. So this is saying we can extend out a unit cube from the origin 0, 0, 0 to the point 1, 1, 1, and all of our intersection points would lie within that cube. Uh, if the ray strikes the plane, yeah, there's not going to be any intersection with the triangle outside of 0 and 1. So the ray only intersects the triangle if b of 0, or x of p minus t x of omega, is greater than or equal to 0 and less than or equal to 1, and vice versa for the y. And we don't need to check the z because we've determined it from the other two components. Okay. It's uh mm,
Did they say which intersection algorithm this was?
this is the ray triangle intersection.
Okay, yeah, because there's one called Mahler Trombor that this one's
I
kind of nice. M O.
It's the one that you copy paste.
Yeah, yeah, yeah.
I'm sorry, I play trombone, so I
M
really had to know if Muller trombone was an actual thing. And it seems like it's just a trombone player.
Nice.
Moller. O with an umlaut, but yeah, I think you'll get it with Mo.
This will probably get me something close to it. What? How do you spell?
Moller.
Well, there's a Wikipedia link in the chat if you really
Yeah,
need to know.
that would be far easier. Yeah, that's Trumbor. Oh, and it's molar. Yeah, I heard. Okay. Anyways, uh, I think this is a fast algorithm rather than just an algorithm, because it does things like without needing to pre-compute the plane equation, where this is trying to introduce barycentric coordinates, a concept that even today kind of makes me go, huh? Whenever I have to think about it. So Uh,
This one does get you very close. Too. If, yeah, this is a nice algorithm for if you're doing a little ray tracer, I think.
definitely. It's good to know X is a point, whereas B is a vector. Is that the structure? I'm not quite sure. Yeah. Oh, there. Okay. Original. So B is kind of like, hey, let's take the original points in there and subtract away the origin. And so it's kind of like redefining the redefining things. Yeah. It's kind of like, yeah. Interpolate vector V and barycentric B. We have our origin X plus or X plus or equal. We do the dot per is this um I'm trying to comprehend what this was representing. Oh, it's this. X is the sum of
It's a
B.
weighted sum of all the components in the vector. Or
Oh yeah, that makes sense. Yeah. Okay. You put it like that. Each weighted by the corresponding element of B. Hmm.
It's one of those like it sums to one. So yeah, when you the
Yeah.
barycentric weights
Yeah, and we can, yeah, and the awesome thing is we can write any point within the triangle as a weighted sum of these three barycentric coordinates. Uh, Barycenter, or the centroid is just a third of each. Um, so I think I understand like the idea. I mean, it's they're weights, so that you blend each point to get a point inside the thing. What confused me the last time I really dove into this with the ray tracer, no, the software rasterizer, that's what it was how you compute the B's. And that's what the tiny rasterizer did not explain well, in my opinion.
Yeah, I've yet to fully understand. Yeah, I couldn't derive that, in a vacuum. I don't think.
Yeah, I'm sure if you spent an evening on it and had Google at your disposal, you could derive it. But like, if you just pulled me aside and said, "Hey, there is a gun to your head. If you don't derive this, I would be unable to." So
How do you know if the point is outside of the triangle?
that's the fun part. Uh, that's a good question.
With the barycentric weights,
Calculate the barycentric coordinate.
Actually,
If any one of them is less than 0 or greater than 1, then it's outside.
it, it's really easy to conceptualize that. Imagine we have X and pretend that's the center of the triangle. We have three vectors going outwards, to V0, V1, and V2. A point outside of it is just a negative weight. So you go backwards along the ray, and that's how you get outside of it.
yeah, and if you think about
You can.
a weight of 0 is
Can I
the weight
draw?
in between V1 and V2. If you're looking at 0 weight on V1.
Yeah, yeah. Imagine it in two dimensions. imagine it on a number line. It's the way you get outside of a blending area is to have a negative coefficient that, brings it outside of it. Oh yeah.
All right.
Smash.
Okay. I see.
Yeah. Um, Pilot triangle is opposite. Yeah, the other thing is, why can't I? There we go. The highlighted region V1, V2, X is opposite of V0. Oh, well, here it explains that. Yeah. So yeah, that's a good way to describe it. If you had a point outside of it and were to draw a triangle from two of the points to your two of the vertices and the point, it would have a negative area, and so your that would be bad. Well, not bad, just not inside the triangle. Okay. Uh, okay. That's a very silly analogy, but I I dig it. Yeah, as a non-native speaker, oh God. Oh, I would be very remiss if this was your only explanation as to what the heck is being described. Um, so they're gonna try to solve the arbitrary triangle by just shifting the arbitrary triangle into the coordinate frame of the unit triangle, which is uh a lot more succinct than flies and peaches, south, north, east, west, all that jazz. Oh, okay.
Yeah, I agree. If you're gonna look at describing it that way, I think a picture would help.
Yes, I think so too. Mm, ah, so this is a important note. Uh, we can distort space as much as we want, but we have to do it linearly, otherwise the coordinates won't line up anymore because it'll have a nonlinear yeah, it preserves straight and parallel lines. If you don't do that, then your barycentrics will look wrong. Or your like texture mapping would look wrong because your barycentric coordinates look wrong.
How does that work with perspective? Because perspective distortion does not preserve
You have
parallel lines.
you have to this actually is covered in the tiny renderer pretty well. I don't want my own. I was hoping it'd show up there. Um, does it do? I think it's tangent. No. Um, okay, this is just the Okay, this is just the perspective. Change of basis. Okay, you can chain them. Great.
I feel like I don't understand tangent space normals very well, and that's something I want to revisit.
What I want to know is how it handles the perspective stuff, and I know we covered it. I'm just not seeing where it's covered.
I want to say it was like maybe lesson 2 there, the triangle rasterization.
Yeah, if you look at a rasterizer,
Don't.
I've seen it before. It's like a little extra math, like maybe a divide, extra
Yeah,
divide somewhere.
yeah,
It's probably in the perspective projection.
yeah. That's what I thought, but I didn't see what I thought was it. Um.
This chapter of that tutorial is bad.
Yeah.
So it's probably in here somewhere, but
You know what? Scratch Pixel is a much better resource. There's a 3.0. Open source. Yay. Uh, um, um, there's a Discord. Okay, I'm sorry. I'm gonna join that real quick because if I don't, I won't remember to later.
Could you send the invite link to?
I will. I will. I will. There. Oh, no, you don't get to see my Discord. Not that there's anything there to see. It's just, it's gonna be recorded. Um, Perspective correct vertex attribute interpolation. So we have to interpolate things correctly, but when we project them, it's nonlinear, so we can't just like interpolate it like before because the distances change. Yeah, this is, I think, what I was thinking of because I've read this chapter and I went, ah, I've subsequently forgot what it was. Okay, here's
Oh, when it clicks.
math.
Okay, that makes sense.
Yeah. I believe one of the things that John Carmack is quoted saying is someone asked, "Hey, can we do perspective correct texture mapping?" And he's like, "Yeah, I can do that," as like a 19-year-old or something like that. And, that was one of the tricks that early id games had that made them stand out was this very good-looking texture mapping in real time, um, on a 280. Anyways, do we want to dive into this chapter, or do we want to just say this chapter explains it and then move on?
I
We
think
should do the latter, I think.
Yeah, okay. Um, so gone through our analogy. We actually described what we want to do. Find the distance t to the intersection point and its barycentric coordinates if the intersection exists. Yeah, vertex position. These first. You can use them to test whether a point is inside a triangle in any space, and we can use them to linearly interpolate in any space. It's TD express the necessary distortion of space to solve the problem without the use of linear algebra. Huh, okay, so it sounds like we'll revisit how we do this later on. Um, okay. Hmm. Okay. Computes the version. Okay. Yes, the cross product of two vectors is an operation that we need to do what we want. Is it going to tell us? Okay, yes, it is going to tell us what a cross product is. Okay, so this is the ray triangle intersection algorithm in pseudocode. We have E1, which is V1 minus V0, and E2, which is V2 minus V0. So these are two vectors from V0 towards V1 and V2. And then we have the normal of the triangle, which we, well, is the norm. So Q is a vector, and it's the cross of omega and E2. A is the dot of E1 and Q. So we dot the omega direction in the normal and it's greater than 0, or the absolute value of the dot product of E1 and Q is less than epsilon, it doesn't intersect it. Okay, so this is implying nearly parallel because we're dealing with computers and not math. So we have to test against a very small value rather than is equal to 0, because a nearly parallel ray will be nearly parallel but not actually parallel. But the way floating point math works means we have to do a less than epsilon, where epsilon is like 0.001 or some very small number. In either case, it's not an intersection, so we return nothing, or we return false. So our vector S is our P minus V0. So we find the vector from the origin of the ray minus V0, and we divide that by A, which is a scalar, and it's the E1 dotted with Q. I'm having a hard time keeping track of all the different letters. SQ aren't. R in our case is the S and E1 crossed over with each other. And then, so this is the lines 9 through 13 are how we derive the barycentric values, and I could not just explain to you why we S and R and W and Q get dotted together like they are.
But to be honest, I know this math and I still get confused about
Yeah.
those symbols now.
What I can say is, because the 3 points of a triangle are actually really like two vectors from a point, we can just define the third point as 1 minus B0 and B1 because it's a blending weight. So that's nice. That I can explain. Anyways, here's a nice diagram of what's going on. We got our V0, we got our E1 and E2 emanating from it, we got our normal out of the plane of the triangle, got our P and omega of our array, and X is our intersection point, and we do math, and then we find out what X is through computing what the barycentrics would be, and then if the barycentrics are, if any of the things are less than 0, then it doesn't intersect it. And if, I guess they can't be greater than 1 because there's actually, yeah, that's a good question. Can a barycentric value be greater than 1?
If one is greater than 1, then there is other less than 0. So it's equivalent. Check this way.
That's
It could be greater than 1 if you're extrapolating.
Well, but to have v0 be greater than 1, that means v1 and v2 have to be negative
Well,
for
one
that
of them will have to
blending
be
rate to
negative
happen.
to compensate, yeah.
Yeah, so
But
okay,
that does happen in practice.
yes, that very good point. I just was wondering why we're not checking for greater than 1 as well, and that's the answer.
Yeah, the thing you wanna ensure is that the weights are normalized.
Mm. Okay. Okay, so cross product is an operation involving two vectors that returns a vector, unlike the dot product, which takes two vectors and returns a scalar.
Wait, you mentioned having those weights normalized. Is that why they check
Oh.
below 0? Because if there's a scale factor, the less than 0 still works. Or I guess
Well, actually, I'm not sure why they're. So in this context, they're just checking if the point lies outside the triangle, which means. Oh, I guess yeah, it's sufficient to check if all of them are either below 0 or
Well, it's not all of them.
yeah,
If
if any
any
of them
of
are below
a
0 or if any of them are greater than 1. But if checking either of those conditions is sufficient, you don't need to check if any are above 1.
so
Because if any are above 1, that
yeah.
implies one of them is below 0.
Uh, uh, this is the textbook definition of a cross product. And while I know this, I'm like, I've seen the pictures where you take a 3x3 matrix and you do the crosses and other things. This has absolutely no meaning to me. Why are we doing why are we doing each of these things? Hopefully they'll explain that. It's useful. It is absolutely useful. It's the way I understand the cross product to work is if you take two vectors and you find the cross product, the third vector is always orthogonal to both vectors.
just as an interesting aside, I learned this talking to one of the people doing the 4D ray mergers. The four-dimensional cross product does not exist. So.
Right. The cross product is only defined in a certain dimensions, and I think 7th is the next dimension that has one.
Yeah. Who knows what that means?
I just know that factoid. I don't know why. I think there's another name for a cross product, and it's is it inner product? Outer product. The dot. Um, exterior
Inner
product.
and outer are like more general terms, though. Like
Yeah.
more than dot and cross.
Okay. Okay, we're starting to get into the weird corners of math that I do not understand. That I probably should, but I don't. I was just gonna try to find a nice picture. Yeah, here's the picture. If you have two vectors A and B, and you find the cross product of A and B, you get the third vector, which is going to be normal. The thing to note is that the order matters. If you want the cross product of B and A, you're going to get the vector pointed downwards because it's not the same. It's what's the property when or you can't change the order of the opera? Non,
Commutative or
yeah,
associative or something like that.
I think associative
Yeah,
sounds right.
associative.
Yeah. So that's fun about cross product. Dot product doesn't care which order you do it in. Cross product does. The cool thing with this is imagine that this is a parallelogram and not a square in a 3 dimensions. This vector would not point in a nice 90-degree orthogonal angles. It'd be like skewed. But
So
it's
it's
just
not associative, it's commutative.
what? Property.
Return to middle school math.
Yeah. Commutative, changing order of operators. Ah. So what's the associative rule?
Associative rule is you can add parentheses to arbitrary pair. That's like matrix multiplication. You can do them in any order, but you can't change them. You
So
cannot swap terms.
yeah. So matrices have the matrix math has the associative property, but not the commutative property. That's good to know. Uh, so yeah, vectors, direction, and magnitude. Magnitude, the cross product vector is equal to the sine of the angle between the vectors times the magnitude of the two vectors. I wonder if you could derive this from the definition of the dot product being the magnitude of the two vectors times the cosine of theta of the angle between them. I wonder. Hmm. Oh, but this is only the magnitude of the cross product vector, not the vector itself.
Yeah, I was gonna say because the right-hand side only returns a scalar. I'm like, how does a
Yeah, I was
scalar
like,
equal to a vector?
yeah, we got the double bars for
Yeah.
magnitudes everywhere. Um,
I
uh,
think this is a way to like calculate the area of a parallelogram. And if you think
yeah,
this way, then this equation just makes sense.
yeah. That's what I remember my calculus 3 class talking about parallelograms and cross products, of which I kind of didn't pay that much attention to because that was not the first time I've heard about cross products, but in the school's curriculum, it was typically the first place students encountered them. Oh, I think I was taking linear algebra at the same time. No, I wasn't, because that was a fall class in the linear and okay, never mind. It was not at the same time. Not that. Mm, magnitude. Twice the area of the triangle whose edges are formed by the two vectors. The magnitude. Um, Interesting that knowing the area gives us another way to compute intersection. Compute the intersection between the ray and the plane. Compute the barycentric coordinates using the cross products to find the necessary angles? Unsigned area of triangles, 1/2 the magnitude of the cross products. Edge vectors. Directions of the cross product. The subtriangle edge vectors in question will be opposite to the original. Space. Where where does M come from? Uh,
Does that say where m equals or is that m minus? It's the
where
bottom.
M equals V1 minus V0 cross V2 minus V0 over magnitude of the same thing squared equals the normal divided by the triangle area.
That's interesting. Discord compresses the equal sign, so it looks like a minus sign.
Oh, you know what? If I did this, it might not.
Oh, yep, I can see it now.
Yeah. If this was like 1080p, it probably render it okay, but I haven't coughed up enough cache to get Discord Nitro boosting our server to allow that. Oh well. So can anyone want to give a shot at explaining? Oh, is this just saying the BI is I plus 2 minus I plus 1 rounding or modulo 3 so that it wraps around. Um, yeah. Uh, is that? Oh, no. Is there going to be a nice visual? Yeah. This is the visual representation of that. So if we
Of
have a
what?
3 by of this line 32 here,
That's
where
more visualization of the calculation of the cross product.
right. I'm just saying that if those seem arbitrary, it's like if you have a 3 by 3, the things you care about are going to be on these things, and you just wrap the values around and you just keep extending it. So yeah, that's what I meant by has a visual. Sarus's rule. The determinant involves multiplication. Okay, I believe you. So this is lots of fun cross product stuff. Um, I'm not quite sure where M comes from. Like, hmm,
I think it maybe is the
oh,
normalization that Jacob mentioned earlier.
oh,
Because they're
is it just the mag?
in 32.
Is it
Are you,
the
are you asking where N comes from or M?
no M?
Oh,
Mama.
M is defined on the last line.
Yeah, and is it saying M is the magnitude of the cross product?
No, it's a normalized cross. Wait, but why is it square?
It's the normal of the triangle divided by the triangle area. So it's normalizing the normal vector of the triangle because the normal vector has to be the as the same as it's pointing in the same direction as the cross product, right?
The denominator shouldn't that be like 2 times? Or I guess I'm not understanding why it would be squared.
No, because this is the normalization function because you're um wait, no, that's right. Uh
Because it's double the area, right?
that's
The
a
magnitude is.
yeah. I mean,
Hmm.
what was the
I'm not sure.
ugh. Yeah, okay. So how are we going to extend this for triangle meshes moving on from this piece of work math that is the cross product? Um, so if we want to do raycasting with many primitives, we just do an algorithm where we test each primitive individually and return the closest intersection found. Very, very crude, but would work. Uh, and a mesh is just a bunch of triangles, so we just have to do a ray triangle intersection on each triangle individually, which is going to be computationally expensive, but that's the way of things.
It's good for you.
Uh, yeah, it builds character. Um, We got the teapot. Hopefully it's the Utah teapot. The unofficial logo of graphics community. Yes, it kind of is. Uh, Speaking of teapots in Pixar movies.
There was a Wikipedia article.
Oh,
That's totally Utah default.
it is. Um, we got the Simpsons 3D episode. We got the teapot in the background. Uh, are there other Pixar movies with teapots in it? Probably, but I won't spend too much time looking for them. Okay. So performance considerations. 15,000 triangles means 15,000 ray triangle intersections per pixel. That means, yeah, a lot. We can simplify things by just not rendering as big of an image or by not rendering as many triangles. Uh, so we can improve things by implementing optimizations. Like if it's in the wrong direction, we'll just, hey, that's not gonna hit it ever. So yeah. Um, a spatial data structure is a tree. Yeah, we'll deal with spatial data structures at a later point. Yes, ray triangle is more expensive than ray sphere because you have to do more checking. Uh, oh, we got some visualization for debugging. Yeah. So when you're trying to debug stuff where you have 15,000 of the thing because you have a lot of pixels or triangles or both, having ways of being able to see specific issues and other things will be helpful. And that's why graphics debuggers tend to be on the visual side where we take a picture or the current contents of the thing and present it as a picture that we can look at. Um, so this is actually a pretty useful technique outside of graphics programming too, but I'm not a regular engineer, so what do I care what architects, doctors, and scientists think or do with their time? Um, yeah. So we have texture coordinates. Um, Texture coordinates are cool. They transform a 3D point into a 2D point on a texture that we can then use to get color information. And that's really awesome because we can take just some flat geometry and turn it into very pretty looking pictures. Uh, um, Texture map. Yeah. Hmm. Yep, we got Yeah. So the cool thing about barycentrics is that we can take the texture coordinates, which are defined at the vertices, and then we can determine where those vertices would be in texture space, then use our barycentric coordinates to interpolate inside the texture space to determine where the pixel should, like the color information should come from within the texture. But I'm not gonna. Does it tell us how to do it here? Yes, it does. We use the, yeah, we interpolate the coordinate, and then we sample the core of the we sample at the texture coordinate that was the interpolated value of the three corners based off the barycentric coordinates. Um, This is us applying a texture to the teapot. Notice the discontinuities as the thing changes over places. So so that's interesting. A way to debug it would be to take the current mouse and find the pixel coordinate, then do the ray trace in that pixel coordinate. And then set a breakpoint when we want. That's useful. Okay, I think that's everything. Hmm?
Take the like all the fragments that would like without doing any depth testing or anything, you take all the fragments that would apply to that one pixel and using that to voxelize a mesh.
Hmm.
I never actually got around to trying.
Yeah, I'm sure there's other ways to debug things, and so beyond what's stated here, and all are equally valid approaches. Well, maybe not equally, but you know,
So I have a question.
shoot.
So the geometry mostly are triangles, right? So when would we use the intersection with a sphere and a plane?
The sphere is just easier when you do a software retracer to first implement sphere. And for plane, well, it's use plane to explain triangles, right?
Yeah, it's it's really a teaching technique here. We explain the triangle, not triangle, the sphere ray intersection because it's simple, and it shows us that what we're trying to do conceptually. We have this, pretty easy to understand definition of a sphere as a shell of points around a center at some distance r, and we rearrange equations, solve it, and then we get a formula for t. Then we do it for the same thing with a plane, and we extend that with triangles by just feedback going on.
It's actually a lot more than that. It's optimization because a lot of objects will have a bounding sphere around them. So imagine the sphere containing the entire teapot. You first intersect with the bounding sphere. And if you don't hit that, you don't have to ray trace against any of the triangles at all.
Yes, completely right. However, from a teaching perspective, I don't think that was intentional because that's an optimization technique as well as the mentioning of or spatial data structures. Where were those? Spatial data structures will be the primary way we figure out whether we need to traverse or whether we need to check ray triangle intersections. So I wonder if the sphere bounding box will be used in our spatial data structure because that's absolutely true.
I just feel like we are so settled with A, B, B these days full ray tracing. I use bounding sphere for calling though, so it's
Yes.
kind of weird, but full ray tracing is same we just settle with AABB basically.
One reason that
I mean,
we use triangles is because it's like the simplest, well, I guess like simplest like surface kind of representation you can get into, unless you had
yeah,
oriented disk from a point kind of idea.
yeah. That's yeah. A triangle. I don't know what I thought. This is what I wanted.
I think is the term
Yeah. It, there any point there is no way to draw a triangle differently. Eh, the 3 points define it explicitly, whereas things like with quads, the quad there's 4 points, but you could actually define a quad the well, there is no plane that goes through 4 points unless the 4 points are coplanar. Yeah. The 3 points of a triangle are always coplanar. They're always a flat surface. Um, and that's a big drawback to more higher kindred shapes.
Speaking of spheres, I think spheres are a prime candidate for modeling light sources.
Mhm.
So if you want to sample a light, then uh, modeling the light like an area light, then modeling it as a sphere is quite efficient compared to modeling it as triangles.
Yeah.
Gotcha. Yeah, all makes sense. And
Is
I have
there?
a
Oh, sorry. Go ahead.
yeah, I just have a real basic question. What's the difference between ray casting and ray tracing?
In this context, ray testing is going to be a component of your ray tracing operation because you're doing the ray
Yeah.
tests to find your intersection
Yeah.
points.
Recasting have other purpose than ray tracing. We definitely need to recast in ray tracing, but recasting is also commonly used for like detecting whether a mouse hit an object or something.
I see. Okay, it makes sense. It's like a subset. When you do ray tracing, you do a lot more than just ray cast. You do that and plus reflections and all that stuff.
Yeah.
Yeah.
Okay.
Um, I'd also like to point out Wolfenstein 3D, which is an example of a ray casting engine, even if that name is unfortunately not very precise. In the in
Yeah,
the
that's what I was confused on because I know about
what
that, but
what Wolfenstein does is it does a single ray cast along the horizontal axis, and it determines the distance into the scene and then draws vertical lines corresponding to that. Before it draws any of the walls, it draws the floor and the ceiling. And so it draws the floor ceiling and then it draws the walls on top of it, uh, more or less. And so you can extend ray casting into both the X and Y dimension, and that's when you start getting things like ray tracing as a different thing. So I'm annoyed that people call raycasting and only mean this when
yeah,
raycasting is a integral component to basically all game development ever. Just because, hey, am I standing on the floor? I don't know. Why don't you do a raycast from your player to the floor? Huh, there's no floor. I don't think you're standing on the floor then. So, or like sound and all sorts of different collision and stuff use raycasts to determine whether you hit or didn't hit something. So I'm annoyed by this overload. I love this image of it's this simplexes is so like whoever made this had too much time on their hand and made it look like some sort of company logo. I I don't know. It amuses me.
Um, Something you said about triangles made me curious. It's probably not something you should try answering. It's just a question if anybody knows. what is the smallest number of things you can use to characterize a triangle? Is it right? Like three coordinates is like in 3D would be, I guess, nine
Nine.
reals.
Yeah.
But
Um,
can we do better? I can think of a way I think that we could do better, but I'm curious if there's like a fundament, like what? Okay, anyway, it's beside the point.
it's a fun
So,
question.
In
I
terms of
don't have an answer.
compression, or because I don't think you can describe a triangle with fewer than 3
Well,
points, but you can certainly do some tricks to like quantize the
no,
information.
okay, yeah. So here's what I was thinking. You can define a triangle as like, so what this is, I was just kept this idea kept occurring to me the whole time from something you said earlier, which is you can define a triangle as like a point, as a sphere that's really far away, um, and a kind of like the center of the triangle, right? So if you have the center of the triangle and you project it onto the sphere that's very far away, so that's just 2 points. If that makes sense.
uh, wouldn't the sphere have to be like
I'm lost.
infinitely far away?
And infinitely
Yeah, to be
large.
perfectly flat, but you could just use that as an approximation, right? So, right, like you could just say it's not on the sphere; it's just the 3 points on the sphere.
How
Yeah.
how would you define those 3 points then on this like that boundary on the sphere that's at in an infinite distance away? I'm sorry,
Three,
I just realized
yeah,
planes are spheres with a infinite radius.
yes, yeah. Yeah, so this would be a sphere very far away, so it would be that's what I'm kind of extending it to. But yeah, I'm not sure if it makes sense. I don't want to waste our time on this, so I'll come back to this afterwards and
Well,
think about it.
I have a oh oh boy. Epic circles. Oh boy, 26 minutes. Um, Hoppus chain, circle inversion, and a whole lot more with this epic video with Simon Pampana. Um,
I love how you
I,
said that.
I believe you. I just would have to see the video first. Um, if we want a complete tangent, but a fun one, this was asked in the lunchroom at my work. Can I get, is there like I need a place to write text. Because this is definitely diverging from ray triangles and ray tracing and stuff. Uh,
There's
I
a
guess
text channel attached to the voice channel.
yeah. So like a is the number of lines going through a point greater than the number of lines not going through that point? And it's a question of infinities, and that I do not know enough about infinities to have an answer to. My gut tells me yes, there is more lines not going through a point than there is lines going through a point. I just well, the way I formalized it is you so imagine all the lines going through that point, um, then each one of those lines can be shifted in the X and Y axis, or like in the X axis left and right if we're in 2D. Okay? And so um, there's an infinite number of lines for every line going through the point. You take a point, you take the line going through the point, and there's already an infinite number of lines not that are parallel to that line. And then you just kind of go, ah, well, infinity times infinity is greater than infinity or something. I don't know enough math.
This reminds me a lot of I don't know enough math either, but it reminds me of measure theory. Maybe that might interest you.
It probably is a measure theory problem. Not to be confused with measures in music theory, which I wonder if there is a similarly named measure theory in music. Yes, this circle is, or this oval is greater than that oval. Uh, uh, hmm. Okay, well, do we have things we want to talk about this week? Things we want to show people have stuff done that they would like to announce or otherwise make hay about? I'm gonna stop sharing my screen unless for the time being.